Would you see the reaction going faster or slower if we doubled the concentration of the reactant? If we have more of this, would it affect the rate? Why? Why? Are you using like a Le Chatelier's principle kind of thing, where if you have more of this, it's going to do that? Think of what does it take for reactants to react and change. They've got to run into each other. They've got to hit each other with enough energy. And we'll talk about that in this chapter, collision theory. But the more of these you have, the more collisions are occurring, the more of these are bumping around and into each other, and so the more frequently they're breaking down and making products. So the higher the reactant concentration, the faster the reaction will go. Yeah?
Shows or show?
Oh, it says experiment shows that this is a first order reaction. So if I double the concentration of N2O5, the rate would double. That's what first order means. If I triple the concentration of the reactant, the rate triples. First order. That's what that 1 is doing there. So if that goes up by 2, then the rate is going to go up by 2. That kind of thing. It's a linear relationship. Okay. Now, we get to do a little calculus now. If you're interested in doing a little calculus, Nilesh, you up for that? Why not, right? What else can we be doing? Okay, good. Amanda, you're good for it? You're out? Okay. Okay. Oh, good. Okay. Okay. You know your integrals?
Yeah.
Good.
Like tomorrow.
Oh, do you? Oh, this is perfect timing. Okay. So we know this is the first. Don't write this because at the top you already wrote that down. First order means that. Remember, this is how the rate is defined: the change in the concentration of the reactant over time. Since it's first order, that's K times N2O5 to the first power. Yeah. That's what I said, the part that I asked you to highlight. You've got to run this experiment lots of times, changing the concentration of the reactant, and you find, oh, when I double the concentration of the reactant, the rate doubles. That's how you would know.
All right, so it's just kind of a given thing.
Yes, right now it's given.
Okay.
Yep, yep. Thank you for asking, too. If any of this doesn't make any sense. Again, none of this really is going to come together for a few days, so just understand that now. But it will. All right. So if we're looking at some time interval, then the deltas change to this D term. If you haven't had calc and haven't done any integrating yet, don't worry about this. You're not going to have to do any integrating, really, because I'm just going to derive these things. That's all that I'm doing. You're not going to integrate anything. But for the derivation, we will. So I'm going to take this relationship. This, remember, what is the first power? I just left the 1 off of it. So moving the N2O5 terms all over to the one side, and everything else to the other side, it's going to look like this. I'm going to move the N2O5 terms to the left. So it's going to be 1 over concentration of N2O5, d N2O5, equals, that negative sign's got to move too, negative K dt.
Do the N2O5s cancel out, or is the N2O5 its own like specific thing?
Say it again.
Like, do the N2O5s on the left?
Oh, yeah. This D is like some infinitesimally small change.
Oh, okay.
Yeah. Now, this is a differential equation. So to evaluate this, we can take an integral of both sides over some time interval t. So that's going to look like this, from 0 to t. And do that on the other side too. Okay, my friends, test review. What is the integral of 1 over x?
ln.
Natural log of x. That's right. Very good. Everybody knows that? Amaya?
Yep.
No, I mean everybody that's going to be taking the test.
ln.
Got that?
Yeah.
Okay.
So like derivatives.
All right, well, That's fine. No big deal. You don't need to do this. So natural, and by the way, I know everybody else in the building, I'm sure, uses lowercase l and n, but I just can't help myself. I'm sorry about that. ln of n205. Now remember, this is over some interval, so this is at time t minus at time 0. So it's going to be like this. At time t minus ln of n205 at time 0. Now this is significant because that was the initial concentration. Time 0 means that none of this had changed yet. So the initial concentration is what I have there. That is significant. Now, negative is a constant, k is a constant. So what is the integral of dt? If I take the negative k and move it to the outside of the integral, now I'm just integrating dt over some time interval. Just t. That's right. Time at t minus time at 0. And since time at 0 is 0, it's just going to look like this. Negative k times t. So we have natural log of the reactant concentration minus the natural log of the initial reactant concentration. This is at some time t. So this number is going to be higher than that number because the concentration of the reactant goes down. So at any time after it starts, it's going to be lower than what it was at the beginning. And then that's equal to negative kt. I'm going to take this, recopy it on the next slide. I'm going to move this term over. See that? Over here it was being subtracted. So to get over the other side, it's got to be added. Notice the kt was negative, and it still is. So it's negative kt plus the natural log initially of the reactant. If we, what's that?
We don't understand this right now, it's okay.
No, it's totally okay.
Okay.
It's all right.
All right.
So don't get uptight and think, oh, no, I'm never going to get this. You will.
Okay.
It'll come together.
Okay.
Even though I do that whole derivation thing just to give folks that are curious the opportunity to see it. You're not going to repeat that. Okay? So now this is the part that you're going to actually use. If we took this data, hello again. Come on in.
So as you guys know, today's the last day for teaching nominations. And Mr. Moore is in the finals. So
For the dodgeball competition, who's playing dodgeball? Are you Andrew? Tim? Good. And? Zainab. You're the first girl that said yes. Great. Do you have an all-girl team?
Yeah.
Oh, make it to the finals. I hope that you do. Maybe we could use this as a dodgeball. Can we practice with this kind of thing? Go ahead.
Anyone like to donate for Mr. Moore?
This group is probably afraid of me. They don't want me to whoop them down in dodgeball, so I would understand if they didn't want to donate.
Thank you. They're going around doing.
That's what was that, Andrew?
You're gonna lose.
Lose the nomination to play?
No. Game. He's trying to bounce back. I'm gonna beat you.
You can't talk smack to me, Andrew. Yeah, that's right. After class, we're going. Okay? So anyway, if you take a look at it, now you haven't really seen a data set with these kinds of problems yet, but what we would see is we can track over different time amounts, we can see what the concentration of the reactant is. So at any point here, the natural log of that equals negative kt plus natural log of the initial. That was the initial concentration. If we plot natural log of the concentration versus time, keep in mind that k is a constant value. That's called the rate constant. It does not depend on the concentration. And this term over here is a constant because whatever the concentration was at the beginning of the reaction, that's what it was. And that doesn't change as the reaction goes on. The initial concentration is what it was. So if we plot this versus time, it turns out that it's a straight line. What's the slope of the line?
Negative k.
It's negative k, right. This is then the equation of the line. This is our y value, natural log of the concentration. T is the x-axis, and then this then is the slope. So it would be a negative slope, because k is going to be a positive number, but it's negative k. And then the y-intercept would be whatever the initial concentration was. If you know how to plot graphs on your graphing calculator, you'll be glad that you know, because you can get through problems a lot faster. When I had these problems due, I go to Excel and I try to run an Excel graph. I'll show you that. Yes, it is that simple. Yep, yep. Andrew?
So for like the class, if we were to write a easy question for like if we know the graph, do we get used the calculator?
Yes, but even so, these problems turn out pretty tedious, and I don't think that I would be able to give you a problem where you have to make, you'll see, I'll do an example problem at the end of the hour, and you'll see how tedious it would be and how not feasible it would be. So I would do things to make those problems faster for you. All right, now I have something written in red. This is important. This is highlighted material. That's why I changed the color on it. When you plot the natural log of the reactant concentration versus time, if it gives you a straight line, that confirms that the reaction is first order. If it's not a straight line, it's not first order. It's got to be another order. It's either 0 or second order in that case. Yeah, that just means the initial concentration. That was at time 0, which means the reaction hadn't started yet. Are we all good with that slide? All right, let me show you just what these problems look like. Number 37. The decomposition of hydrogen peroxide was studied, and the following data were obtained. So this is the reaction for the decomposition of hydrogen peroxide. When it decomposes, it makes water and oxygen. So the reaction was run, and whoever did this problem monitored the concentration of hydrogen peroxide as the reaction proceeded. So you see that it started high at 1 molarity, and then as time went on, the reaction went to the right and the concentration of the reactant went down, which you would expect. The question is, it's asked you to determine several things. Number 1, the rate law. And if it doesn't tell you what kind of rate law, it implies that means differential rate law. Second, it asked you for the integrated rate law. Third thing was the value of the rate constant. That's the K value. So we're calculating all those things. Plus, it says, calculate the hydrogen concentration at 4,000 seconds. So yeah, we need another data point down here. What would the concentration of it be down there? We would have to do a graph and be able to determine what that is. All right, now just so you can see, this is what an integrated rate law problem is going to look like. You're going to have data of concentration versus time, and you have to plot that data. Not the data though. Remember, if you want to know if it's first order, you have to take the natural log of each of these and plot them versus time. If that gives you a straight line, then that's a first order reaction. So that's what I'm saying here. To know if it's first order, you're going to have to plot natural log of the peroxide over time and just observe and see if it's a straight line. And then also it asks us at the end to find what the concentration was at 4,000 seconds. You'll have to use whatever rate law you determine. So I'm kind of leaving a big gaping hole in the explanation of this problem. We're going to move on and see 0 order and second order. I did first order first because that's the most common. You'll see more first order reactions than any other order. Can I move on? I'm hoping you're not writing all this down.